Betelgeuse, situated 642.5 light-years from Earth and known as the shoulder of Orion, has long been one of the most fascinating stars shining in our visible sky. A red supergiant with a surface temperature of roughly 3,000 Kelvin, millions of years old and now deep in the final stage of its evolution. It has burned through fuel at an extraordinary rate throughout its lifetime. Recently, its outer layers have turned erratic. It has dimmed. It has brightened again. It has expelled material, and scientists have openly debated its possible transformation into a supernova. But here is the detail that changes everything. Because Betelgeuse lies more than 600 light-years away, the light we see today actually left that star over 6 centuries ago. In simple terms, it is entirely possible that Betelgeuse exploded decades ago, and we would still have no idea. The signal must travel those 642.5 years before it reaches Earth. That delay turns a future event into a present uncertainty. And when a red supergiant reaches the end of its life, the result is never subtle. A supernova marks the culminating event in a star's existence, an exponential surge in size and temperature followed by an immense release of light and energy. Studies indicate such an explosion can briefly illuminate an entire galaxy. For Betelgeuse, the energy release could surpass everything our sun will emit across its whole lifetime. So what would that actually mean for us? Let's start with the first and most unsettling reality. Betelgeuse sits roughly 642.5 light-years from Earth, a distance so vast that every piece of information we receive from it arrives fundamentally delayed. Light does not travel instantly. It must cross hundreds of light-years before anyone on our planet can observe or study it. This means the image of Betelgeuse we see tonight in the night sky is not current. It is historical. What we observe right now is the star exactly as it appeared more than 6 centuries ago. The true importance of this distance goes beyond how far any explosion's effects might travel. It also determines exactly when we would learn that such an explosion had even happened. From our perspective, it is entirely possible that Betelgeuse has already gone supernova, and we remain completely unaware simply because the light has not yet finished its journey. That delay creates a strange situation where the event could already belong to our past, while still lying in our future observationally. Betelgeuse, also classified as Alpha Orionis because of its status as a red supergiant, is firmly in the final stage of stellar evolution. Larger stars consume their fuel far more rapidly than smaller ones, and Betelgeuse exhausted its hydrogen long ago while swelling to enormous size. Astronomers believe it may eventually become a Type II supernova and possibly collapse into a neutron star, depending on its exact oxygen and neon content. There is even a chance it could end as a white dwarf. The star's distinctive red color comes from its relatively low surface temperature of about 3,000 Kelvin, typical of red supergiants approaching the close of their life cycle. Its erratic outer activity and repeated changes in brightness have kept astronomers locked in ongoing theoretical debate about what comes next. The question is not whether Betelgeuse will die. The question is only when. And because of the immense distance, our awareness of that exact moment will always lag behind by centuries. To grasp the potential scale of a Betelgeuse supernova, the material draws a direct comparison with the most devastating nuclear events in human history. In 1945, toward the close of the Second World War, the United States detonated 2 atomic bombs over Hiroshima and Nagasaki within days of each other. More than 110,000 civilians perished in what remains one of the most tragic chapters ever recorded, and the only 2 times nuclear weapons have been used in large-scale conflict. Decades later, on April 26, 1986, the Chernobyl nuclear power plant disaster unfolded during a power test that went catastrophically wrong, destroying the surrounding town. These incidents stand as the most consequential nuclear events caused by human action and forever change how humanity perceives radiation and sudden energy release. Yet according to the document, second after second across the universe, nuclear-scale explosions happen with even greater force. These events release enough radiation to obliterate entire planets in moments. But they take place hundreds of thousands or millions of kilometers from Earth, far enough that their consequences never touch us directly. The only steady source of space radiation that actually reaches our planet is the Sun, whose output is safely filtered by the ozone layer. The comparison exists for one reason: to scale our understanding. Human nuclear events are catastrophic on a planetary level, but in the cosmic context, they are nothing more than tiny flashes compared to what stars produce naturally. When a massive star like Betelgeuse reaches the end of its life, it does not simply fade away. A supernova is the culminating event of stellar death, an explosion in which the star dramatically increases in size and temperature before unleashing an extraordinary burst of light and energy. Various studies referenced in the document show that the luminosity of such an event can temporarily light up an entire galaxy. In the specific case of Betelgeuse, estimates suggest its supernova could release more energy than our Sun will produce over its entire existence. Supernovae are therefore regarded as the largest explosions known to occur in space. A historical precedent mentioned in the document is the explosion that created the nebula RCW-86, witnessed by Chinese astronomers in the year 1054. The intensity of that supernova was so extreme, it remained clearly visible even during daylight hours. That single fact reframes the entire scale of stellar detonation. If a supernova can outshine the daytime sky from immense cosmic distances, then the explosion of a nearby red supergiant becomes far more than an abstract astrophysical event. It becomes a phenomenon with visible, measurable, and historically documented precedent. Compared with Hiroshima, Nagasaki, or Chernobyl, the energy involved is not merely greater, it is incomparably greater. For decades, Betelgeuse has been famous for its external activity and its periodic fluctuations in brightness. The star would lose part of its luminosity and later regain it over time, a pattern recorded since its earliest observations. In recent years, however, the behavior of its outer layers grew markedly more erratic. Between 2019 and 2021, something unprecedented took place. The star dimmed dramatically after ejecting an immense cloud of material following a powerful outburst. The event rattled the scientific community. A red supergiant already in the final stage of its evolution suddenly losing brightness on that scale could not be ignored, especially with ongoing discussions about its potential transition into a supernova. The dimming was not subtle. It was observable, measurable, and significant enough to capture worldwide attention among astronomers. Given that Betelgeuse is the closest star of its type to Earth, and one of the finest subjects for studying the late stages of stellar evolution, its behavior quickly became the center of intense analysis. The concern arose not from speculation, but from direct observation. A star already known to be nearing the end of its life had just displayed striking instability. The timing alone sharpened the debate about its future. In 2021, scientists established that the material expelled during the event was racing outward at more than 200,000 miles per hour, roughly 320,000 kilometers per hour. Although such debris was expected to travel vast distances, the extreme cold of space rapidly condensed and slowed the particles. This detail proved critical. It did more than explain the dimming. It offered a clear window into how stellar ejections actually behave in the vacuum of space. The expelled mass created a cloud that temporarily blocked the star's visible light from Earth, giving the impression that Betelgeuse was fading away. At the same time, the event became an invaluable opportunity for modern astrophysics. The ongoing evolution of Betelgeuse has delivered enormous scientific value, because it remains the best available subject for examining how massive stars behave in their final stages. Its proximity makes it uniquely observable compared with other red supergiants. The dimming episode was therefore both alarming and enlightening. It displayed instability perfectly consistent with a star approaching supernova. Yet it also revealed that expelled material can behave in ways that limit its long-term expansion due to rapid condensation in the cold of space. The event did not confirm an explosion was imminent, but it strongly reinforced that Betelgeuse is undergoing significant and measurable change as it nears the end of its life. If Betelgeuse were to begin its supernova process, the document explains that the initial phase could involve an immense release of energy. That release, depending on its scale and propagation, could potentially affect electrical networks in parts of the world, or even globally, in a manner similar to an electromagnetic pulse, commonly called an EMP. The comparison is not offered as certainty, but as a possible consequence directly linked to the magnitude of stellar energy discharge. Radiation from the explosion could also trigger geomagnetic storms, which in turn might damage electrical grids, create unusual visual effects in the atmosphere, and disrupt or decalibrate satellites, especially GPS systems. The mechanism described focuses on radiation interacting with Earth's magnetic field and technological infrastructure rather than any physical destruction. The concern is not planetary obliteration, but disruption. Electrical systems could face instability. Satellite networks could malfunction. Atmospheric phenomena could become visible. The chain reaction remains conditional, yet it clearly outlines a technological vulnerability connected to high-energy cosmic events. Even though these probabilities are described as particularly low, the scenario demonstrates that a supernova of sufficient magnitude is not entirely disconnected from terrestrial systems. It is distant, but not irrelevant. Once the red supergiant begins its supernova transformation, Betelgeuse is expected to shine roughly 9 times brighter than the full moon, an event that would be unmistakably visible from Earth. Scientists watching for such an occurrence would look for a sudden surge of neutrinos arriving from the direction of Betelgeuse as the earliest warning of the explosion. After the initial burst, as the light slowly fades, the remnants of the supernova could stay visible in the sky for several years. The event would not be momentary. It would linger. While the document notes that the likelihood of severe electrical impact remains low, it highlights another certainty: social and cultural upheaval. Humanity has always tended to react with fear and alarm when faced with physical or atmospheric phenomena that lack an immediate explanation. The sudden appearance of a red supergiant exploding in the night sky and shining brighter than the moon would inevitably command global attention. The event would be not only astronomical, but profoundly psychological. Public reaction could include fear, speculation, and misunderstanding, particularly among those unfamiliar with the scientific context. For this reason, the document stresses knowledge as a crucial virtue, suggesting that understanding these events is essential to prevent unnecessary panic. The explosion, if it occurs within observational range, would be a cosmic spectacle, but its greatest impact may not be physical damage. Rather, the profound reaction it would trigger across human society. Betelgeuse is not just another star in the sky. It is a red supergiant in the final stage of its evolution, a celestial body that long ago exhausted its hydrogen, expanded to enormous proportions, and now behaves with increasing irregularity. It has dimmed. It has expelled massive clouds of material. It has reminded astronomers that massive stars do not fade quietly. They end violently. And the most unsettling part is not the explosion itself. It is the delay. At 642.5 light-years away, Betelgeuse exists for us only as a historical image. What we observe tonight is the star exactly as it was more than 6 centuries ago. If it exploded decades ago, we would not yet know. The signal would still be traveling. That reality transforms a distant stellar death into an event suspended between past and future, visible only when the light finally completes its journey. If and when that moment arrives, the consequences described are not planetary annihilation, but measurable impact. A burst of energy that could resemble an electromagnetic pulse in effect, radiation capable of generating geomagnetic storms, potential disruption to electrical grids and satellite systems, a brightness 9 times stronger than the full moon dominating the sky. A surge of neutrinos arriving first as silent messengers from a dying star, and afterward a fading light that could remain visible for years. The physical probabilities of severe impact may be low, but the social reaction would not be. History shows that humanity responds with fear to unexplained atmospheric phenomena. A supernova visible to the naked eye and brighter than anything seen in generations would ignite conversation, speculation, and alarm across the globe. And that is why knowledge matters. Because when that light finally reaches Earth, whether tomorrow or centuries from now, it will not be a surprise to those who understand what they are looking at. It will be the natural culmination of stellar evolution, a process as old as the universe itself. Betelgeuse will eventually die. That is certain. When we see it happen is the only uncertainty. If you want to stay informed about real cosmic events that could reshape how we see the universe, subscribe and activate notifications. Because the next signal that reaches us from deep space may not just be light. It may be history arriving 642 years late. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.